In the early hours of a September morning, 1940, this plane, a Heinkel HE-111, was making its way towards London, carrying 2 tons of bombs to the densely populated city. It may well have reached its destination, if not for the early warning systems the British military home defence had created. A network of radar stations all feeding into a central operations room where incoming raid information was ratified and mapped on a gigantic chart of Britain. It was from this room in Bentley Priory that all RAF commands during the Battle of Britain were made. This was a frantic but precise procedure. Every minute that passed was a crucial minute stolen from the pilots. Vital time needed to gain altitude to meet the enemy on a level playing field. This groundbreaking air defense network allowed Britain's defenders to be in the air at interception altitude within 10 minutes of the first signs of invasion on the radar screens. This would not have been possible without aircraft capable of quickly gaining altitude to meet their foes. The Spitfire is the icon of the Battle of Britain, capable of climbing 760 meters per minute, taking them, at minimum, 4 to 5 minutes to reach their target's altitude. The Spitfire was a nimble interceptor, a plane that could rapidly gain altitude and proceed to fiercely defend its airspace. To do this, it needed to be powerful, maneuverable, and capable of packing a punch. Some of the greatest engineers of World War II worked on this fighter, and the designs they came up with changed the course of the war. This is the insane engineering of the Spitfire. Despite its patriotic fame, the groundbreaking nature of the Spitfire's design is difficult to comprehend today. In a world where we are long accustomed to all-metal, low-wing fighters, the Spitfire, despite its undeniable elegance, may seem mundane. However, when the Spitfire first swept through airfields in 1936, the RAF still operated aircraft like the Gloucester Gauntlet and the Hawker Fury. Biplanes were the norm for fighters of this era. The stacked wings increased the lift the aircraft could generate while making them stronger and better able to withstand the G-forces of maneuvers. But they generated a lot of drag. The Spitfire was made possible by new, powerful engines and new, revolutionary, age-hardened aluminium alloys, freeing the Spitfire's chief designer, R.J. Mitchell, to get creative, setting out to create a plane capable of outrunning and outturning any foe. Turn performance is essentially measured by the minimum turn radius a plane can achieve. A tighter turn radius gives a fighter aircraft an edge in a dogfight. To understand what affects the radius of this turn, we first need to understand how an aircraft turns. To begin a turn, an aircraft will roll in the direction of the turn. This is called the aircraft bank angle. This splits the lift the plane is generating into 2 components: a horizontal component that causes the plane to turn, and a vertical component that keeps the plane in the sky. A steeper bank angle will increase the horizontal component and decrease the turn radius, while stealing lift from the vertical component. This vertical component needs to equal the weight of the aircraft, or the plane will lose altitude. To compensate for that, the pilot will deflect the plane's elevators downwards to increase lift, but this also increases drag. This increase in drag means the pilot will also need to increase engine power to maintain speed. The maximum turn possible that won't result in loss of altitude or speed is called the sustained turn performance, and it's affected by the weight of the aircraft, the excess power available from the engine, and the design of the wings. To excel in battle, the Spitfire needed the perfect wing, and Mitchell did his absolute best to give it just that. R.J. Mitchell had plenty of experience in designing sleek, high-performance aircraft, designing the Supermarine S5 that won the Schneider Trophy in 1928. There was some deliberation on the shape the Spitfire's wing would take, with some early designs like this one from 1934 showing a straight taper, unlike the iconic elliptical wing it eventually took. This would have been vastly easier to manufacture, but the shape a wing takes has a huge effect on performance, in particular lift distribution, and the elliptical wing provides the ideal lift distribution to minimize induced drag. Induced drag occurs when high-pressure air from underneath the wing travels to mix with the low-pressure air above the wing over the wing tip. This creates a vortice at the wing tip that saps kinetic energy away from the plane. This elliptical lift distribution minimizes this effect, but R.J. Mitchell is quoted in Alfred Price's The Spitfire Story saying this:
"I don't give a bugger whether it's elliptical or not, so long as it covers the guns."
The reduction in induced drag is often cited as the sole benefit of the elliptical wing, when in actuality it barely made a dent in the overall drag characteristics of the plane, which was not worth the added difficulty in manufacturing. The real benefits of the elliptical wing came from the planform's slow reduction in chord length. Take a straight tapered wing. Its chord, the width of the wing, steadily decreases from the root of the wing, steadily reducing the area near the fuselage that can be used to fit equipment. The curve of the ellipse, on the other hand, maintains the width of the wing close to the fuselage, and then drops off more rapidly towards the wing tips. This provides ample room inside the wing to fit the landing gear, guns, hydraulics, radiators, and wing support structures. The room provided to fit a strong but lightweight wing spar is a key benefit that allowed the Spitfire to take daring turns without worry of structural failures. The engineers of the Spitfire had a delicate balancing act to perform. Increasing the strength of a wing often requires adding weight, and adding weight decreases turn performance, climb performance, and increases fuel consumption. The Spitfire's wing is not perfectly elliptical. Its trailing edge turns inwards more rapidly than the leading edge. This was done primarily for structural reasons. The main structural support of the wing is the wing spar, and in the Spitfire, it runs perfectly along the quarter chord of the wing. The quarter chord is located, as its name would suggest, a quarter of the way up the width of the wing. It is the aerodynamic center of the wing, where the overall lift of the wing acts through. If the wing was perfectly elliptical, it would be impossible to place this wing spar along the quarter chord, and the overall lift force would, as a result, be behind the wing spar, instead of directly over it. This would create a twisting motion on the wing that would require additional strengthening and weight. This is why the trailing edge curves in as it does, to adjust the quarter chord's location to be in line with the wing spar. Much was done to minimize the weight of these support structures. The bending force the wing needs to resist decreases as you travel down the wing, so the spar can reduce in strength and weight throughout the wingspan. Manufacturing a complicated shape was not particularly easy in the 1940s. Today, we can manufacture single parts to shapes engineers of World War II could only imagine using CNC milling machines. To allow the strength of the wing spar to decrease, it's constructed from simple nested square extrusions. The upper and lower spar booms were constructed from 5 concentric aluminium square sections, which were cut and placed inside of each other like this. This wing was an engineering masterpiece that gave the Spitfire incredible handling characteristics. When we compare the Spitfire to the Bf-109, its nemesis during the Battle of Britain, we can start to make some real deductions about the effect this wing had on the plane. The wing area of the Spit is noticeably larger. This affects a performance metric called wing loading, which is simply the total mass of the aircraft divided by the wing area. This affects the turning radius of the aircraft, A heavier aircraft with smaller wings will have a larger wing loading, and as a result will have a larger turning radius. The Bf-109 wings were much smaller and thus had a higher wing loading, and so the Bf-109 had a larger turn radius than the Spitfire. While the space afforded by the Spitfire's wings allowed it to fit 8 Browning machine guns inside the wing, or as later variants featured, 2 larger 20mm cannons and 4 of the smaller 7.7mm Brownings, all mounted inside the wing and outside the propeller arc, which reduced the engineering effort needed to integrate them. A luxury the Bf-109 did not have. The engineers at Messerschmitt were forced to use more complicated designs to integrate armaments. 2 machine guns mounted above the engine could fire through the propeller blades with an interrupter gear timing the triggering to ensure they did not strike the blades. A cannon could be fitted behind the engine, which would fire through a hollow tube that ran through the inverted V12 engine and through the nose of the propeller hub. Later variants attempted to correct the disparity in firepower by mounting guns inside the wings, but there wasn't enough room for ammunition, so a belt feeder was run through a chute from the fuselage to the guns. This wasn't a reliable mechanism. Some variants did include gun pods mounted below the wing, which negatively affected the plane's handling. The Spitfire's primary role was an interceptor. To do this, it needed a powerful engine and light airframe. The most important factor for climb rate is power to rate ratio. Creating a powerful engine that could fit into a small airframe required some of the best minds in Britain. The Merlin engine of the Spitfire went through many iterations over the war, with the constant goal to squeeze more and more power out of the 27-litre displacement engine. Displacement meaning the volume of the cylinder swept by each piston. The displacement of an engine has a huge effect on the total power output. Power is derived from fuel burning to create heat, which creates pressure on the cylinders to do work. To increase power, we need to increase the amount of heat energy released, but we can't just add more fuel without adding more air to burn it. There is an optimum air-fuel ratio, about 12:1, 12 parts air to 1 part fuel. This gets even more complicated for aircraft that fly through various altitudes, because the air pressure decreases as we climb. Air pressure drops by half at 5,500 meters, which would half the oxygen available to burn the fuel. To combat this, the Merlin featured a supercharger to increase air pressure. Air began its journey into the Merlin engine through the air intake located underneath the fuselage. From here, it first passes the carburetor, where fuel is mixed into the airstream. The Spitfire utilized a float carburetor. Float carburetors use, as the name would suggest, a float. The float works similarly to the float in your toilet cistern, detecting the fluid level and controlling a valve to keep it at the optimum level in the carburetor tank. This became an issue for the Spitfire when German pilots learned the engine would cut out in a negative G maneuver. A negative G maneuver would force the float down and open the valve, flooding the engine with too much fuel. The Bf-109 engine utilized direct fuel injection, a more complicated system that required 12 plungers, 1 for each cylinder, cams to time the fuel injection, and geared power from the engine. A more complicated solution that allowed German pilots to perform negative G dives to evade pursuit, while Spitfire pilots needed extra time to perform a roll before diving, which ensured the dive was made in positive G, giving German pilots precious time to escape. After passing the carburetor, the air entered the supercharger compressor, where the air was compressed before entering the piston, increasing the power output of the engine. This system helped the Spitfire squeeze out extra horsepower from their 27-litre engine, rivaling the power of the much larger 34-litre DB601 engine fitted into the Bf-109 during the Battle of Britain. However, early Merlin engines featured a single-speed, single-stage supercharger, the speed of the supercharger being determined by the gearing ratio coming from the crankshaft. This forced the engineers to design the supercharger to work at the optimum speed and compression ratio for a particular altitude. We can see this when looking at power curves that plot the engine power versus altitude. The early Merlin 3 reached peak power around 10,000 feet before quickly dropping off. You may notice that power output is actually lower at sea level, despite the ambient air pressure being higher here. That's also a result of the supercharger speed being fixed. In order to prevent the engine from being overpressured, there was a throttle on the air intake that gradually opened as the plane gained altitude. While the Spitfire had excellent power at its optimum altitude, its Bf 109 foes during the Battle of Britain had superior power at lower altitudes, because they featured an ingenious device that allowed their superchargers to vary their speed. Their supercharger was placed at a 90-degree angle to the engine, and power was transferred to it with a fluid coupling, which uses a fluid to transfer power from the engine to the supercharger. The input shaft causes a fluid inside the coupling to rotate around the casing with a pump, which in turn causes a turbine attached to the output shaft to turn. This method of power transmission allowed the supercharger to operate at various speeds because the amount of oil inside the coupling was controlled by a separate pump, which gradually increased the amount of oil inside the coupling as the plane gained altitude. This prevented the supercharger from overpressuring the engine and gave the Bf 109 engine superior power at lower altitudes. This gave the Bf 109E variant, which was most widely used during the Battle of Britain, an edge over the Spitfire. While the Spitfire could outturn the 109 had a better power to weight ratio, which allowed the 109 to sustain a climbing turn to outmaneuver a Spitfire on its tail. British engineers were well aware of this issue prior to the Battle of Britain, and development began on a two-stage, two-speed supercharger for the Merlin engine in mid-1940. This allowed the supercharger to operate at two different speeds via a gear change, but also introduced a second impeller which increased the compression for even better high-altitude performance. This increased compression caused an increase in temperature of the air that would negatively affect engine efficiency, and so an intercooler had to be introduced to cool the supercharged air before entering the piston. This intercooler removed 33% of the heat added by the supercharger. Removing more heat would have been beneficial, but there is a balancing act here. To remove more heat, the plane needed a larger radiator to dump that heat to atmosphere, and a larger radiator would result in more drag, which negated the power increase. The radiator design, in fact, was one of the chief ways the Spitfire managed to squeeze so much power out of its smaller Merlin engine. German engineers had noted how much smaller the Spitfire's radiators were and knew exactly why. In one meeting between the chiefs of Germany's aviation development, Messerschmitt noted that the Spitfire's radiators were half the size of their own, while the head of German engine development explained to an indignant government official that to reduce the radiator size would require higher coolant pressures, which their engine couldn't tolerate without leaking. The British had developed high-pressure, high-temperature coolant systems for their high-speed racing engines to compete in races like the Schneider Trophy. The Germans were prohibited from participating in these races by the Treaty of Versailles, and so were left behind in the development of this vital technology. Increasing the pressure of the coolant allowed the engineers to raise the operating temperature of the coolant without it boiling. An increased temperature difference between the radiator and the outside air increased the rate heat could be radiated away from the plane, and this allowed the Spitfire's radiator to be much smaller. This did require the radiators to be stronger and thus heavier, but the reduction in drag more than made up for the increased weight. The Bf 109 and Spitfire were formidable foes for each other, and the difference between life and death, more often than not, came down to the skill of the pilots and the strategic advantages the British had in fighting over their home soil. The Battle of Britain was won on small margins, and the engineers of the Spitfire did everything they could to give the Spitfire an edge in battle. But it, and the much more numerous Hawker Hurricane, would not have stood a chance without the systems and procedures on the ground that allowed them to get into the air day after day. Radar, data processing, mapping, chain of commands, pilot training, and even fuel octane ratings all played a role in winning the Battle of Britain. And I explain it all in our Nebula original series, The Battle of Britain. Many of the animated sets, including the custom-made operations room at Bentley Priory that you saw in this video, were created for that series. And that's the level of quality you can expect from all our Nebula original series. There are currently 4 episodes available for you to watch right now, with even more on the way, along with our 7-part Logistics of D-Day series. Or you could watch my favourite recent original by Wendover Productions, covering the history of Wake Island, a tiny remote island in the middle of the Pacific with a rich history in aviation and World War II. If you want to support this channel, watch our videos ad-free, including sponsor messages like this, and get to watch incredible exclusive documentaries from independent creators, join Nebula now by signing up for the Curiosity Stream and Nebula bundle deal for just $14.79 a year. $14.79 for an entire year membership, giving you access to both Nebula and Curiosity Stream's massive catalogue of educational and entertaining videos and documentaries.